forces in equilibrium. Let's once again think of my favorite yellow ball. Now, just to make it easier to imagine, let's say this ball is on a smooth table. It's just at rest. If I now want to pull it to the left, I want to apply a force on it to the left, say a force of 2 newtons. Okay. Now then my friend wants to apply a force to the right. Okay. Also 2 newtons. But clearly the two forces would balance or cancel each other, and the ball will still stay at rest. We can describe this by saying that these two forces are in equilibrium, which just means that they are balanced. The word equilibrium is just a difficult word to say that the forces are balanced. Okay, so the forces acting on this ball are in equilibrium. Okay, you can say that if you want to be more precise, perhaps. Okay, so let's now think of a slightly more complicated situation. Now, in this example, the two forces are along a straight line, so it's quite easy to see when the right side force is equal to the left side, they're balanced. So that's quite straightforward. But what if we now think about forces in 2 dimensions? So let's say this is my ball again, but this time I'm looking down from the top. Okay, so this is my table, and I'm looking down from the top. Okay, so my table is here. Just to make it easier to imagine, so I have a table, maybe where I have my dinner or lunch. So I have a ball on my table, and now let's say I now apply a force in this direction, a force of 3 newtons. Okay. Now my friend wants to apply a force at right angles. He wants to apply a force of 4 newtons. So clearly they're not in equilibrium. Right? They're not in equilibrium. The ball will start moving somewhere, in a direction roughly in between the two forces. So the question now is, if I want to apply another force to balance those two, we can roughly guess that the force must be in roughly the opposite direction, maybe somewhere there, and maybe it must be some value. Not exactly sure what direction and what value, but somewhere there, right? If we actually get a ball and try this out, I'm sure we can find another friend to balance the ball. But what we want to do is to work out a way to actually calculate the magnitude of this force and its direction. How can we do that? What we can do is this. We can think about this plan, right? Why don't we first find the resultants of these two forces, right? The resultant, so that's the combined effect. So the resultant of these two forces is a single force, roughly in that direction, and then we just balance that force. Once we've found that force, all we need is an equal and opposite force equal and opposite force, a force in the opposite direction of the same magnitude, and that's it. That's the answer. That force must balance these two forces. So to make this a little bit more more concrete, more definite. Now, if I want to find the resultant of those two forces, the way to do it is, there are two ways to do it. Let me sketch out one way. Is to draw a parallelogram with those two forces as the sides. In this case, since their right angles are parallelogram, is just a rectangle. And then draw a line joining the tails of the two vectors, where the two tails meet, to the opposite corner of this rectangle, and that's my resultant. That's my resultant. So once we know that we can do this, we can then calculate the magnitude of this. Now in this case, this is a right angle, so we can use Pythagoras theorem, okay, to calculate this, and you'll find that the force is actually 5 newtons. Okay, using Pythagoras theorem. And then you can use say tangent. You can use tangent to find the angle, to find the direction. Okay, right, so we can find this angle and use this angle to tell us the direction. So once we have found this, we can then we would then know what force we need to balance the the original 4 and 3 newtons. All we need is a force that is equal and opposite to this. So that would be that. Right, just directly opposite. Okay, must be the same magnitude. So 5 newton. And the opposite direction, how would we describe the opposite direction? That would be, say, if I draw this line along the 3 newton force. So the direction 5 newton force must be must also have an angle of theta here. Okay, so must be the same angle as this angle. So if we know theta, we have the description for this force, the full description, the full answer for the force that balances those two forces. So you can see, as you can see, it's a bit more involved. It needs a bit more work, a bit more calculations than this first example where both forces are in a straight line. Now from this point, we can summarize this idea. We can actually summarize this idea into a simpler method. Okay, let's see how to do that. Now, as I just mentioned, maybe I didn't mention that, but okay. So anyway, finding this resultant force by drawing the parallelogram is just one way. It's just one way to find the resultant. Now there's another way, which is by drawing a triangle. So let me draw the triangle. Okay, so instead of drawing this parallelogram, I can also find this 5 newton force like that. I'll draw it out here. So that's my 4 newton force. Okay. And that's my 3 newton force. So what I'm going to do is I'm going to imagine 3 newton force, taking this 3 newton force and moving it, okay, so that its tail touches the tip of the 4 newton vector. Alright, I can move this like I move a real object, a real arrow. Only thing is, I'm not allowed to change its direction when I move it. Let's see if I can do this. this. Oops. But there is another way to add those two vectors, 4 newtons and 3 newtons, and that's by drawing a vector triangle. So let me start by drawing 4 Newton vector. So imagine that I take this 4 Newton vector, I take this 4 Newton vector and I move it here. Okay, I'm allowed to move it as long as I don't change its direction. And I'm going to take the 3 Newton force. Imagine that it is a real object, a real arrow, and I'm going to move it up there. Again, I must not change its direction. So that's the 3 newtons. So I've just moved it so that the tail of one arrow touches the tip of the other arrow. And now, to find the resultant using this method, I must join the tail of the first arrow to the tip of the second arrow, all the way there. Okay, and that would be my resultant. If you compare this triangle with this half of the rectangle, you find that this triangle is really the same as this half of the rectangle. And that's the simple reason why this method works, because it's basically the same thing as doing the rectangle, but I'm just drawing just drawing this triangular half of it. So therefore, since that's a right angle, in this method we can use the same Pythagoras theorem and find that this is 5 newtons. And then we can also find the angle here or there. Okay, so we have just remembered the method for finding the resultant vector using a triangle. So that's the resultant vector. Now, back to what I was hoping to find right from in the beginning. I was hoping to find this force, this force that will balance the 4 Newton and 3 newtons. And in this first method that I described, I said that after you have found the resultant of the 4 and 3 newtons, this 5 Newton force, all you need is to take its opposite direction and describe the opposite force. And that gives you the answer. So if I then come back to this triangular method of adding the two vectors. Once I've found the resultant 5 newtons, then I will know, I can just say that the force needed to balance this 5 newton is just 5 newton in the opposite direction. Okay, so this means I can now make up a method to find this resultant force. So let me draw out the 4 newtons and 3 newtons again. So these are my starting force. Let's say in the beginning, okay, we know we are given that there is this 4 newton force and there is this 3 newton force. Alright, down here the 3 newton and 4 newtons. So I'll just move the two arrows so that the tip of one touches the tail of the other. And when I want to add those, I use this method by joining the tail, the first arrow, to the tip of the second arrow. Now, but if I want to find the force that balances the 4 and 3 newtons, I need the opposite direction, right? The force, the same magnitude in the opposite direction. So rather than joining the tail of the first arrow to the tip of the second arrow, what I can do is I can join the tip of the second arrow to the tail of the first arrow. And if I do that, I just get a force which has the same magnitude as this resultant, and it is in the exact opposite direction. And this must be my answer. So what I have just done is this. What we have just seen is a method. Alright, we have just discovered a method to find the force that you need to balance two other forces. Okay, and we can always use this method just if you have three forces. Okay, in order that they are balanced, all we need is to check that they form a triangle. Now, so what I've just said is actually something that is useful in finding force in checking whether three forces are balanced. Okay, and also in deciding whether they're balanced. So we describe this picture by calling it a vector triangle. A vector triangle. Okay, so what is this idea? We can describe this whole idea by saying that forces in equilibrium, okay, forces in equilibrium form a vector triangle. Need an L dash.